Okay, welcome back, my dear friends. Let us continue with class 12 mathematics, chapter 4. One of the last topics that we have for class 12, that is, we have already now learned much about matrices, how we add, multiply matrices. Then, of course, we have come to determinants, where we have learned about what is a determinant. We have also learned about how to find out the minors, cofactors, the adjoint, and of course inverse of a matrix using determinant method, and when the inverse of a matrix exists, when it does not exist. Now in this one of the last topics that we have for this unit 2 chapter 4 of unit 2, we will see how we can actually apply determinants and matrices to in our daily life. In other words, how do we solve problems using using determinants and matrices. One of the basic applications of determinants and matrices is to solve a system of linear equations using inverse of a given matrix. Now up to 10th standard, we have already seen how do we solve a system of linear equations. System of linear equations up to two variables of the form generally ax plus by plus c equal to 0, a2x plus b2y equal to c2. So basically we have already seen up to like our 10th standard how we solve a system of linear equations up to two variables. So there were some methods that we have used, like substitution method. If you remember, we had learned about substitution method, we had learned elimination method, then we had learned cross multiplication method. Then of course we have even learned graphical methods also. So these were all the methods that we had actually learned up to our 10th standard on how to solve a pair of linear equations that were generally given to us, a pair, or we can have maybe more than that also. Now this determinants and matrices can also be used. That means this is just another tool which you will have now in your arsenal to solve system of linear equations. That means now by substitution method, by elimination, by cross multiplication, by graphical, now you can add like by determinant and matrices. Using determinant and matrices also, you can now solve a system of linear equations. In fact, using determinants and matrices, it will help you to actually solve bigger equations with more variables. Of course, using all these methods also it can be done, but using determinants and matrices, like when you have more variables, 3, 4, 5 variables, then using determinants and matrices, it will become a lot easier. So these are just tools, another weapon in your arsenal which you can use anytime. So now, but before that, we had actually seen that for any pair of linear equations, first comes, like for example, if you have a pair of linear equations like this, a2x plus b2y equal to c2, then we also have to check for their consistency or inconsistency. That means like this pair of linear equations, there can be three cases that might arise. That is, in first case, they may have a unique solution. They may have, second case, they may have infinitely many solutions, or the third case, they may have no solution. So we have already seen in our lower classes that when a pair of equations have a unique solution or infinitely many solutions, then those system of equations will be called as consistent. And if they have absolutely no solution for those pair of equations, there is no common point which for both the equations, then in that case we say that the system of equations will be inconsistent. So let us not forget to keep that in mind, consistency and inconsistency. Consistency when we have at least a solution, a unique solution, or infinitely more solution, that is more than one solution, and inconsistent when we don't have any solutions at all. So since the topic is all just about application of that only, another tool which you will be another tool which we'll be using now to solve different pairs of linear equations, that this properties will also hold. Now let us take some example, like consider the system of equations. Let's say a1x plus b1y plus c1z equal to d1, a2x plus b2y plus c2z equal to d2, a3x plus b3y plus c3z equal to d3. So here we have like three equations, a system of three equations with three variables. So definitely this might look a bit complicated to get it solved using substitution or elimination method. Of course it can be done, but today let's learn how can we use determinants and matrices to get it done more smoothly, maybe more easily. So now if we consider the matrix A to be the matrix of all the coefficients of the variables from the equations, that is a1 b1 c1, a2 b2 c2, a3 b3 c3, a set x, a matrix x of the variables in the given equations, and another matrix B of the constants of the given equations. Then it can be clearly seen then the system of equations can be written as ax is equal to b, product of a into x equal to b. Remember, this is a 3 by 3 matrix, this is a 3 by 1 matrix. So when you go for a 3 by 3 and 3 by 1 matrix, your result will be a 3 by 1 matrix, which is exactly the matrix B, that is a set of this the matrix of the constants of the given equations. In other words, this, of course, this concept comes from the concept of matrix multiplication. So those who have already learned the concept of matrix multiplication, I believe that you will understand how these equations can be written in the form of matrices. So this is how the equations can be represented. Now let's see for different cases, like now for case 1, that is like, because after that maybe 3 linear equations may be given to you. Now after that you may be told to solve, but we are not sure whether we'll be having some solutions or not, or they may have a unique solution, they may have infinitely many solutions, they may have like no solutions at all, isn't it? So blindly just proceeding into and getting the solution, sometimes you will not end up anywhere. If it doesn't have any solutions, how will you get any solution? So for that, what happens is there are certain steps which we can do to check. Now the first case is like when the determinant of A is not equal to 0. That means, what do we say this matrix to be? Then it is called as none, singular, none singular matrix, singular, sorry for my handwriting, non-singular matrices. Then in this case, of course, we know that in this case inverse of A, of course, inverse of A will exist. Now in this case, what you will have is we will have a unique solution. That means we can proceed further and find out the solution for this equations, that is, in other words, find out the values of x, y and z, which will satisfy the system of equations given to us. Now we will proceed with that equation that we have, ax equal to b. I'll just give you the derivation part also, so what happens and how it happens. So here what we do is we pre-multiply by A inverse to both the sides. I'll not write down again, I've already said, like we are going to be pre-multiplying by A inverse of A on both sides. So in that case, by associative law, A inverse A into X, A inverse of B. So A inverse A will be identity matrix that we have already seen from properties of invertible matrices, which implies X will be A inverse of B. That is, this is the ultimate equation. That is, you can, for a system of linear equations of 2 or more variables, when the solution exists, that is, when we have a unique solution, the solution can be found using determinants and matrices by this statement, that is the matrix X, which consists of the variables of the given system of equations, will be equal to nothing but the product of the inverse of the matrix A, that is how we use matrices, and the product of the inverse of the matrix A and the product and the matrix containing the constants of the given system of linear equations. Now let's go for some more cases, like case 2. Now we are left with first case, that was a unique solution. Next case, infinitely many solution, then we have no solution. So this case is done. Infinitely many solutions, how can we find out? That is when the determinant of A is equal to 0 and adjoint of A into B is not equal to 0. Then in that case, of course, we say that the system of equations has no solutions. And case 3, that is again when determinant of A is 0, that is, in other words, singular matrices, and adjoint of A into B, the product of the matrix of adjoint of the product of the matrix of adjoint of A and B is equal to 0, then in that case we say that the system of equations will have infinitely many solutions. So from these 3 cases we can clearly see that only when determinant of A, only when the matrix is a non-singular matrix, then in that case only we'll be having a unique solution. Then we can proceed and use this statement and find out or solve or get the solution of the system of linear equations by, we generally call this method as maybe like by the matrix method. But when there are singular matrices, then 2 cases will arise. That is, you will proceed to find out the adjoint of the matrix A, get its product with B. If it is not equal to 0, then in that case no solution. If it is equal to 0, then in that case, of course, infinitely many solutions, but there is no point in proceeding further. So that is where you will be stopping your solution. So most of the cases that will be given to you will be of this case, but sometimes you have to be careful for case 2 and case 3 only. So in the next videos we will be mostly focusing on matrices, on system of linear equations where we have unique solutions. So in the next video I'll teach you 1 or 2 problems how to solve system of linear equations using matrix method, and after that I'm very sure that you will be able to do any kind of matrix problems, you will be able to solve any kind of a system of linear equations using the matrix method very smoothly. So I believe that the next videos also will be more helpful. If you have liked these videos, please share it with your friends, subscribe to us, and if you need any solutions on any exercises, please leave a comment below, or you can even email to us. From the team of Teach Nagaland, we thank you.